A solar prominence is a large, bright, and often loop-shaped structure consisting of relatively cool, dense plasma suspended above the Sun's surface by magnetic fields. These structures are part of the Sun's outer atmosphere, known as the solar corona. Solar prominences are visually striking during solar events, such as solar eclipses, when they become visible along the edges of the solar disk. Key features of solar prominences. Composition. Solar prominences are composed of ionized gases, primarily hydrogen and helium, forming a plasma. Despite being cooler than the surrounding solar corona, they are still extremely hot, with temperatures ranging from about 5,000 to 100,000 degrees Celsius, 9,032 to 180,032 degrees Fahrenheit. Magnetic fields. The formation and dynamics of solar prominences are closely tied to the Sun's complex magnetic field. Magnetic fields play a crucial role in shaping and supporting the prominence structures, preventing them from collapsing back onto the Sun. Classification. Solar prominences are classified into two main types based on their appearance. Quiescent prominences. These are long-lived and relatively stable prominences that can persist for weeks or even months. Eruptive prominences. These are more dynamic and can undergo sudden and dramatic releases of energy, leading to solar eruptions known as coronal mass ejections, CMEs. Eruption mechanism. The eruption of a solar prominence, leading to a coronal mass ejection, often involves the reconfiguration of magnetic fields. Magnetic instabilities or the release of magnetic energy stored in the Sun's atmosphere can cause prominences to erupt. As the magnetic fields reconnect and realign, they release a tremendous amount of energy, propelling the prominence material into space. Process of solar prominence eruption. Magnetic instability. The Sun's magnetic field lines are constantly shifting and interacting. In regions with complex magnetic configurations, instabilities can develop, leading to changes in the magnetic field structure. Magnetic reconnection. Magnetic reconnection occurs when magnetic field lines from different regions come into contact, leading to a realignment of the magnetic fields. This process releases a significant amount of energy stored in the magnetic fields. Eruption and coronal mass ejection, CME. The release of magnetic energy triggers the eruption of the prominence material into the Sun's outer atmosphere, known as the corona. This explosive event is often associated with the release of charged particles, forming a coronal mass ejection. Solar wind impact. The material ejected during a solar prominence eruption can be directed toward the Earth, influencing space weather. If a coronal mass ejection reaches Earth, it can interact with the Earth's magnetosphere, potentially causing geomagnetic storms and auroras. Prominence dynamics. In some cases, solar prominences may partially or completely fall back to the solar surface after an eruption. The interplay between magnetic forces and gravitational forces determines the fate of the prominence material. Observing and studying solar prominences is essential for understanding the Sun's dynamic behavior and its impact on space weather. Instruments such as solar telescopes and space-based observatories provide valuable insights into the complex processes occurring on the Sun's surface and in its outer atmosphere.